Hi guys, I'm Sai Krishna. Let us look at question number one. In question number one, we are given joint density function fxy x comma y as 1 plus xy by a, and we are given the conditions for x mod x and mod y. So in the part one, we are told to calculate the value of uh, we were told to calculate the value of a. So let us look at the solution for this. So I've written down fxy of x comma y as 1 plus xy by a when mod x is less than 1, mod y is less than 1, and this is equal to 0 otherwise. Okay, so in the part 1 we have to calculate the value of a so that it remains a valid joint density function. So for this to happen, the limit the condition is integral minus infinity to double integral minus infinity to infinity fxy x comma y is equal to 1, dx dy equal to 1. Sorry, I forgot. Dx dy is equal to 1, which means that I'm substituting the value of mod x and mod y here. Minus 1 to 1, minus 1 to 1, 1 plus xy by a dx dy equal to 1. So it is integral minus 1 to 1, integral minus 1 to 1, 1 by a dx dy plus minus 1 to 1, minus 1 to 1, xy by a dx dy is equal to 1. This means that 1 by a x between the limits minus 1 to 1, because when I'm integrating dx it becomes x, and then there is an integral minus 1 to 1, and there is the dy integral, plus integral minus 1 to 1 y by a x's integral is x square by 2 between the limits minus 1 to 1, and there is an integral element dy. The sum is equal to 1. So this becomes 1 by a. When I substitute the limits, this turns out to be 2, and then there is integral minus 1 to 1 dy plus integral minus 1 to 1 y by a. When I substitute the limits, this becomes 1 by 2 minus 1 by 2. So this is 0. Dy is equal to 1. So basically this whole term tends to 0, becomes 0. So here this is 1 by a. 2, when this dy is integrated, it turns out to be y, and when I substitute the limits, 1 plus 1 equal to 1, because this is 0. So this is 4 by a equal to 1. That implies a equal to 4. We have got the value of a as 4. So let us look at the part 2 of question number 1. In part 2 of question number 1, we are asked to see if xy are uncorrelated or not. For uncorrelated, e of xy must be equal to e of x into e of y. So let us calculate the value of each one of them and see if they are uncorrelated or not. First, let us calculate the value of exy. So for this is minus infinity to infinity, minus infinity to infinity. Xy is xy into fxy x comma y dx dy. This is the e of xy. So this is because mod x and mod y are given as less than 1, so I'm integrating it between the limits minus 1 to 1, minus 1 to 1, xy 1 plus xy by a as 4 dx dy. So let us calculate it with respect to x first. So this is minus 1 to 1, and this is minus 1 to 1. So let us separate the terms so that it becomes easy for us to calculate. Plus double integral minus 1 to 1, minus 1 to 1, x square y square by 4 dx dy. So this is equal to minus 1 to 1, minus 1 to 1. X is integral. So okay. So x is integral is x square by 2. So this becomes x square by 2, and the y is a constant here. So this becomes y by 4 dy. Okay. And this is integral -1 to 1. This is basically the I will substitute these -1 and 1 in this. -1 to 1 y square by 4, x square integral is x cube by 3. Between the limits -1 to 1, dy is there, dy term is there. Okay, this is equal to integral -1 to 1. When I substitute 1 and -1 here, this turns out to be 0. So we can ignore this one because 1 by 2 minus 1 by 2 is 0. Let us calculate this one. So this becomes -1 to 1, and y square by 4. This is 1 by 3 minus of -1 by 3. Yeah. So this is dy. This becomes equal to -1 to 1, 2 by 3 into 4, the denominator, y square dy. So this becomes equal to -1 to 1, 2 by 12, y square is y cube by 3. So let us substitute y cube by 3 between the limits -1 and 1. So this becomes 2 by 12. Sorry, this is 2 by 12 into 1 by 3 plus 1 by 3. So this becomes equal to 2 into 2 by 9 into 12. So this is 4 3s are sorry, this is 3 because 2 by 3, this is 2 by 3. So this is 1 by 9. So we have calculated the value of E of xy as 1 by 9. So similarly, let us calculate the value of E of y here first. E of y can be calculated as double integral minus infinity to infinity minus infinity to infinity y into xy x comma y dx dy. So this is equal to -1 to 1, -1 to 1 y into 1 plus xy by 4 dx dy. So this is equal to integral -1 to 1, -1 to 1 y by 4 dx dy plus integral -1 to 1, -1 to 1 xy square by 4 dx dy. Okay, so this is equal to integral -1 to 1, integral -1 to 1. Sorry, let us so the y by 4 is a constant when we are integrating it with respect to dx. So it is x between the limits -1 to 1, and there is a dy integral, dy element. So this is -1 to 1, x dx is x square by 2 between the limits -1 to 1 y square by 4 dy. Okay, so this is -1 to 1 y by 4, this is 1 plus 1 dy plus integral -1 to 1. So 1 minus 1, this is 1 by 2. So this is 0. So we can basically not consider this term. -1 to 1 y by 2, because y by 2y by 4. So this is y by 2 dy. So this is equal to y square by 4 between the limits -1 to 1. This is 1 by 4 minus 1 by 4. This turns out to be 0. So 0 into anything is 0. So we can clearly see that E of xy is not equal to E of x into E of y. That means that in x comma y are not uncorrelated. So in this way we have done the question number 1 part 2. For the question number 1 part 3, as they are uncorrelated, that implies that x comma y are not independent. Okay, so let us look at the part 4 of question number 1. So we are told to calculate the joint density functions of x square and y square. So x square, y square. Suppose x square is w and y square is z. Okay. So we have to calculate the joint density function. So the joint density function can be given as f z w of w comma z is equal to mod j here, and f xy of root w comma root z. That means that I have taken the roots here, plus by mod j fxy of root w minus root z plus fxy of minus root w comma root z by mod j plus fxy of minus root w minus root z by j. Okay, so let us calculate the value of mod j first, because that eases the things. So here that is dou w by dou x, dou w by dou y, dou yeah, so dou z by dou x, sorry, I was thinking dou z by dou y. Yeah, this is the, so here it is 2x 0 0 2y, so this turns out to be 4xy. So let us keep this aside. So we can write we can write f wz of w comma z as what can we write as? It can be written as 1 plus root w root z by a should be there, so by 4, and mod j is also there. Mod j is 4 root w root z. Okay, as this is common, the denominator is common, so let us consider the numerator only first. 1 minus root w root z, so there's a plus here. Okay, plus 1 minus root w root z plus 1 plus root w root z. Okay, so this turns out to be, I can cancel out this term, this term, this term, this term, this term. So it's basically 4 by 4 4 root w root z. So 4 and 4 cancel, so this is 1 by 4 root w root z. So I can write as 1 by 2 root w into 1 by 2 root z. So as we know that f of, so in this way I've calculated the joint density function of x square and y square, and then for the fifth part we have to look at whether they are independent or not. So for that we know that f of fzw of w comma z can be written as fw of w into fz of z. So this can be written as 1 by 2 root w into 1 by 2 root z respectively. So this means that they're not dependent on each other. So this means that w comma z are independent. that implies that x square and y square are also independent. So hence, in this way I've calculated the question number 1. Thank you.